All right, so the next talk is by Felix, and he will be talking about the design and implementation of a cognitive overlay system based on FBMC.
Yeah, thanks. So, hi, my name is Felix, and I'm working at the Communications Engineering Lab at KIT in Karlsruhe. And I'm going to talk about, as Phil said, about the design and the implementation of a cognitive overlay system, which we did for the IEEE DICE-band Spectrum Challenge earlier this year in Baltimore. So for those of you who weren't there to attend or didn't hear about it, I'm going to give a short overview over the DICE-band Spectrum Challenge, what its motivation was, what the challenge setting was, and who the other competing teams were. And then I'll go into our solution and how we tackled the different problems and tasks that were given by the challenge, before I go into a conclusion. So first of all, the Spectrum Challenge. The Spectrum Challenge set out to benchmark important cognitive radio techniques, so situational awareness, interference mitigation techniques, and of course, agile and high throughput waveforms. And all that in a, at least somewhat, realistic scenario you can realize at a conference over the air. The setting you were put in as a contestant was basically the setting that you were the secondary user who had to share time and frequency resources with the primary user who was not to be interfered with, so kind of a classic scenario. The tasks, therefore, were twofold. First of all, you had to identify your the transmission patterns of the primary user. You had to learn its behavior by observing. And then, in the second phase, as it was called, you had to show or to demonstrate a secondary user solution that actually optimizes its own throughput while not hurting the primary user. Okay, so that was the setup that was given at the challenge. So there was a primary user actually running on user XT10s, which ran a unidirectional link. The primary user transmitter was delivered packets from a central database. Those were delivered over the air. Receiver received them and sent them back to the database, which then calculated throughput and packet error rate. Same throughput also provided the secondary user with packets and checked the throughput. For the design of your secondary user solution, there was actually only very few constraints. Basically, you had a maximum of 2 antennas available per device. And you had, of course, to use the same spectrum, which was 10 megahertz wide and centered at about 4 gigahertz. So what was the primary user like? The primary user was actually completely radio-based. It was a custom packet generator block, which then fed directly into the GeoDigital's stock OFDM, mod, and DMOD chain. The primary user divided the entire 10 megahertz band into 4 2.5 megahertz channels and used them according to a so-called one of 10 so-called scenarios which defined the transmission pattern. Those were known beforehand, so it was sure that the primary user would only use one of those 10. But those were kind of very different. So there were scenarios where just a single random channel was used with deterministic interpreted packet delay, so that was pretty simple. Then there were scenarios where multiple channels were used in a random hopping manner, but still with a deterministic interpacket delay. Then there was a scenario where really every channel was used synchronously with in a back-to-back manner. And to make it a little more complex, there were also 3 scenarios that were actually really random, with 4 channels being used independently, where the time between frames was based on a Poisson distribution with different means. So now to the actual challenge and how it was benchmarked. The challenge was divided into 2 so-called phases. The first phase was all about situational awareness. So you didn't actually have to transmit anything during this phase. You just had to observe the primary user and detect which one of those 10 scenarios was in use right now. And the score was also calculated very straightforward. It's just a fraction of time you had the correct situational awareness. So you had to classify and then report your classification result back to the database. Of course, the primary user didn't just use one scenario the entire time. It changed its transmission patterns every 15 to 30 seconds randomly, and that phase went on for an entire 10 minutes. So then there was a second phase, which was benchmarked independently. From the primary user perspective, not much to change. That worked actually pretty much the same, but now the metric was not to know it's the current scenario he's using, but to actually achieve throughput, so transmit, and avoid interference. So also the score was made up of two components. So there was, first of all, the throughput you achieved, but secondly, there was also a metric that catches the interference you caused. And as you can see, the primary user satisfaction, as it was called, declined exponentially with interference. So if you do the math, you'll see that if you only cause 10% packet loss, your overall score will be multiplied with a factor of 0.3. So it declines rather fast. If you made it lose like 50%, you didn't really have to care anymore if you would win this. So it was really important to not cause any interference. We weren't alone at the challenge. That would have been kind of boring. So there were other teams that participated, and those were three. First of all, there was Trinity College Dublin. They also participated in the 2015 version of the challenge and were also very successful back then. Then there was Drexel University with Lockheed Martin, and last but not least, the fourth research center from Greece. Because we're at GRCon, I had a look at what they used for their file layers, and it turned out that two of them were actually using liquid DSP, and Greece and us and the primary user were using radio-based solutions, which is, I think, quite a good coverage for radio at this event. And they were all using OFDM, just as we were using something different, but I'll come to that in a second. But first, let's look at the phase one, so where it's all about classifying the primary user. Our approach was rather simple, admittedly, but it was also quite robust. In the first step, we just did an energy detection on each subband and applied an adaptive threshold, which is just based on the energy we measured in between bands, where we didn't expect any signal energy. These now binary occupied, non-unoccupied signals per subchannel were then used to extract so-called frame events, which were basically a tuple made up of a start of frame time and a subband index, which was occupied. These were then used to extract features. Features we used were channel occupation, how many and which channels are being used, what's the mean time between frames, what's the variance between frames. The variance was especially important for distinguishing truly random from the deterministic scenarios. And one very important trade-off we had to consider at this point was, of course, the feature estimation error versus the delay. So the more precisely we wanted to estimate the features, the more frames we needed to consider, the longer became the observation window, and that, of course, caused delay. And we'll see that this delay was actually very crucial for the outcome of this phase. The final scenario estimation was then done through a decision tree, so a handcrafted decision tree, so just a simple if-else construct. And the features were evaluated in order of decreasing robustness. So first channel occupation, then the mean time between frames and the variance. And the successive estimations were also used to increase some kind of a confidence value. But with this, you had basically to consider the same trade-off as before. Because you could slower in the end. And of course, you had to feed back your result to the challenge server. And that is what it looked like in GRC. Pretty easy. You start with the radio, then you have an FFT, then the energy detection, which extracts the 4 channels and binarizes the result. Those go into the frame detection. This then creates the tuples, which go into the feature extraction. In this case, we looked at 50 frame events to create our feature vector, which then went into the scenario classification, which is, as I said, a really simple block. This is actually a embedded Python block, which then did the estimation and packed that into a message and sent it back to the database. How well did it work? actually, it worked, even though being very simple, pretty well. And we were the first team to compete because the benchmarks were done successfully. And we saw a GUI and we were like, oh boy, we're gonna win this. This is working so well. And I mean, it was working well, but we still ended up third because we had only 98% accuracy in our estimation. So we did the math and we realized that those missing 2% were actually exactly the time, the delay we had in estimation these scenarios. So this is a point where we probably should have and could have optimized more. A team that did this much better, actually, was Trinity College Dublin, and they won this one. And they also deserved to win this one, I guess, because they had a really cool solution. They had a completely different approach. They computed spectrograms based off the input signal and interpreted it as some kind of a image classification approach and then threw deep learning at it. And that obviously had a much lower delay. Okay, so this phase was kind of disappointing for us, but there was still a second phase that was to be competed at. And this one was the agile secondary user phase. As I already said, that we were the only one not to use OFDM. We're using FBMC. So why FBMC? What is FBMC? FBMC stands for Filter Bank Multi-Carrier, and you can think of it as some kind of an evolved OFDM. Basically, you could also see OFDM as a filter bank multi-carrier technique where the pulse is a rectangle and the pulse shape is some kind, not some kind, it's a sink. The FBMC I'm talking about is using pulses that are much better localized in frequency. So they achieve a much higher out-of-band attenuation, which is really important for this case and makes it suitable for cognitive radio applications and many more, but especially here. FBMC has actually been a large part of the work of a former colleague of mine, Sebastian Kozlowski, at our lab. And so he initiated GRFBMC, which is available on GitHub. So go there, clone it, and check it out. It's actually really performant. It runs in real time with over 20 megahertz instantaneous bandwidth on really commercial off-the-shelf laptops like the one I have here. Actually, this is the laptop we had at the challenge, so we didn't pack a lot of hardware there. It contains really state-of-the-art algorithms for synchronization and equalization, and also a very nice filter bank kernel. So aside of the modulation, what did make our transmitter cognitive? The logic basically consisted of two steps. First step, not very cognitive, get payload data from the server and pre-modulate frames. This was just done to reduce the delay in a signal chain in the end, because it was all about being fast, of course. In the second step, and this is kind of the heart, or you could say the brain of the system, we had the so-called cognitive allocator, which actively found holes in the time frequency domain. So what needed to be done in order to achieve this? First of all, the scenario classification that ran in the first phase just ran on at the same time. So we had to get the pattern the primary user was using. In order to achieve this in the second phase, however, we had to filter out our own frames. So it had to run even when we're transmitting simultaneously. We actually did that just based on the length of the frames. So that was kind of easy at this point. But now we had the pattern the primary user was using, but we had no notion of where we are in that pattern. So we needed some kind of temporal alignment, you could say. And for that, we used the frame events we were generating anyway. So this provided us with the real-time information to take the pattern and shift it in time so we know when there are frames, and for most importantly, when the next frame is to be expected. So we could proactively place our frames in the time frequency domain. So this would work pretty well if there's a stationary scenario, right? But the whole challenge was about being dynamic, and the primary user changed its scenario every 15 to 30 seconds. So we had to find a way to cope with this. And what we did, because we wanted to avoid interference at any rate, is that we took a very conservative approach. So we checked for each incoming frame event if it actually matched our expectation. And if it didn't, we just blacklisted those channels, waited until the estimation stabilized again, and then resumed our operation. So this is a block diagram of how the system looked like. So in the upper part, you can see the cognitive transmitter. And the upper branch of that is what you actually saw before as GRC flow graph. So the radio and the energy detection, the frame detection, and the scenario classification. But now the result of the scenario classification is no longer used to report back to the database, but fed into the cognitive allocator, just like the frame detection result. And this allocator then takes the pre-modulated FBMC frames and puts them in the right spots before everything is delivered to the radio. On the lower part, you can see the receiver, which is not cognitive, but still quite cool because it's FBMC. So it's the radio, followed by some timing synchronization, which is based on Kazakh sequences, as they're used in LTE. Then there's channel estimation, channel equalization before the actual FBMC frame demodulation follows, and then the packets are delivered back to the database. You might notice that there's no frequency synchronization in here. I didn't just forget it. Actually, we use GPSDOs on both ends of the link, and we realized that this made our frequency offset so low that actually the channel estimation and tracking took care of that. Because we spread pilots all through the frame, and that just worked. And it saved us some computational load. So this is the configuration we actually used during the challenge. So as I said, 10 megahertz for subchannels. We used 128 subcarriers, 111 of that for data modulation. We had a modulation order of 16, so 4 bits per symbol. The payload length was 3/4 of a kilobyte, and that made a total frame length of 1.7 milliseconds. Basically, longer frames are better for FBMC because the long pulses just need some time, and that's overhead, and you want to reduce that overhead. The maximum throughput we could achieve, so net throughput, just payload, considering synchronization overhead, channel estimation overhead, and interframe spaces we had to use, brought us to a maximum throughput of 14 megabits per second about that. And we actually achieved about 12, even when there was a primary user running, so we were quite happy with that. This is a picture of the monitoring display that was used during the challenge. So on the left side, sorry for the bad picture quality, by the way. So on the left side, you can see the throughput, so in red. So the line at the bottom, you could say, is the throughput of the primary user. And in blue, you can see the throughput of our system, actually. And then there's the timer. But the more interesting part is on the right. Because that is, as you might have already noticed, that they just use GRX. There you can see the spectrum and the waterfall plot. So let's have a look at the spectrum in the upper part first. I selected this because you can nicely see how well localized the spectrum of our FBMC frames is. It's really narrow. The band edges are really narrow. And yeah, they're also a little wider because we need to use less guard carriers. And so you can see 3 of the FBMC frames and 1 primary user OFDM frame, actually, on the second channel from the right. What you can see in the time frequency domain in the lower part is actually how a scenario transmission looked like. So we started with a scenario where the primary user was using actually all 4 channels. The primary user frames are the narrower ones. But you can see that our allocator was still able to put our FBMC frames, the wider ones, in between. But at some point, like in the middle of the magnified area there, the primary user changes its scenario, which is instantly recognized by our cognitive allocator because the frames didn't match the scenario anymore. So it stops transmitting, waits until the classification stabilizes again. You can see the new scenario is one where only 2 channels are used, the left one and the one right of the middle. And 2 are actually unoccupied. And the moment the classification is stable again, the allocator starts to put frames really back to back in those channels, but also interweaves them in the other channels. And this is why we really achieved high throughput. In this case, it was about 1.2 megabyte per second. Yeah. Is that right? Yeah. So about 10 Mbit, 9 Mbit. Okay, so how did this phase pan out for us? Actually, pretty well. We had quite some headroom actually before the next one came. And that was, even though they used liquid DSP, which ramped up its constellation to, I think, up to 128 points. So they had quite high spectral efficiency. But the problem with especially Drexel's solution was that it caused a lot of interference, which was due to some power control issues, but also to the OFDM spectrum nature. I asked the organizers to give me the exact numbers that captured the interference, and the primary user satisfaction in our case was actually 0.99 something. So we basically caused no interference at all, which really showed us that our approach worked, while Drexel had something like 0.01, and that really cost them like 2 orders of magnitude in their score. So we actually won this phase, which made us happy again. And this also brings me to my conclusion. So I presented you the design and the details of our cognitive overlay system, which we based on FBMC. It performed pretty well in both phases of the challenge, mostly due to the proactive allocation of our frames, and which avoided causing interference. And I want to stress again that this runs on commercial off-the-shelf laptops with B210s, for instance, and there's absolutely no hand tuning required. This works out of the box. I mean, I can't vouch for any USB 3 chipsets you might have on your device, but it works for this laptop. Also, of course, this has not just been my work. This has been joint work with Sebastian Müller, Sebastian Kozlowski, and Niklas Kwerbu. Some of you might know them. And we also made the code for our solution open source and published it. And also the challenge framework is being published, so you can increase, you can build upon those solutions if you want. We can have a look into them, compare them with our solutions. That's really the idea of the entire challenge. For the future, there's, of course, still work left to be done. First of all, you could reduce delay, which was kind of the central problem of the entire thing. And one approach for this might be to put you could say, delay the critical path or the delay sensitive parts onto the FPGA, for instance, using RF-NOC. Of course, at that moment, you can't no longer use the B210s, but yeah, that's probably what you would have to do. What we're actually doing right now is experimenting with other different classification techniques and kind of benchmarking them, because I think that's rather interesting, and especially Dublin's solution showed us that there's still some improvement that can be done. Yeah, so that's about it from my side. If you have any questions, I'm happy to answer them. Thanks.
Are there any questions?
So you mentioned for future work, you wanted to look at using distributing your processing to RF, not potentially to reduce delay. Did you actually state any delay numbers?
I did not actually, but we had like 1 millisecond of delay between, let's say, receiving the end of a frame, reacting to that, and getting on the air. And luckily, this was pretty consistent So, I mean, it would have been great if it would have been shorter, but it was pretty deterministic, you could say, and so we actually could work with that and just integrated that at some point where we calculated our, let's say, headroom until the next frame would come.
It's a non-technical question, but I'm here. So you've published all the source code for this, which is a great thing. Can you give some word of advice or encouragement to other researchers? You know, like how come you can publish all your source code and others cannot? Like, can you just like give a couple of words of advice or encouragement towards other researchers to do the same thing?
Yeah, I mean, I think it's always great to have such things. I mean, especially because in terms of FBMC, that's some kind of a next generation modulation scheme, and it's really helpful to not have to implement everything again if you want to compare that. And I mean, it's not that trivially actually. I mean, a lot of work went into GRFBMC. First of all, algorithms. Secondly, performance. Yeah, I think that just enables a whole new range of, let's say, or comparisons that are not as easily feasible if everybody has to implement everything himself again. And I mean, this one is really, you can really install it and have an over-the-air link with acceptable bandwidth out of the box. And I think that's a cool thing to have. And yeah, that extends, I guess, to many projects.
Yeah, can you say a little bit more about the modulation type, your filter bank multi-carrier, kind of where'd it come from, what's the prognosis, are others interested in using it?
So, yeah, I mean, I didn't say much about it, but again, the good thing about FBMC is that it's has a very low out-of-band radiation, so you can maybe use it for asynchronous uplink activities where OFDMA naturally has its problems with ICI. This is probably the prime application. Therefore, it's very suited to fill spectrum holes because you don't have to leave that much space or guard carriers next to other systems. That is kind of the prime application. It has been considered in several 5G research projects, and there has been one consortium that has probably bet on FBMC. I'm actually, was it 5G now? I'm not sure. Yeah, was there another question? Another part of the question? Oh, actually, it's pretty old as far as I know. It was like, I mean, Saltzman was important in this case, and that was like in the 60s, if I remember correctly. And but I think it just became feasible in the recent years, so it's really interesting. Yeah.
Any more questions? All right, let's thank our speaker.